Today we're going to talk about barometers and how they work. Barometers are a way to measure pressure. Now there are lots of different units to measure pressure. We understand the idea of pressure. When one molecule strikes another, then that creates a certain pressure. So we know that when molecules collide into the sides of the containers, they definitely create pressure. And the unit for pressure is a unit of force distributed over some unit of area. In the metric system, the SI system, we would say it's equal to a Newton of force spread over a square meter, and that's equal to a Pascal. Now, standard atmospheric pressure, that's all the air above us pushing down on us, exert a pressure of 101,325 pascals. Generally, we write that as 101.3 kilopascals. In terms of a common term for that, we would say that 1 atmosphere is equal to an atmosphere. And we're going to learn that it will push the mercury in a barometer up 760 millimeters, which is basically the equivalent of a unit called 760 torr. And we'll talk about what a torr is and where that name came from. So here's our different units for measuring air pressure. Again, air pressure, when measured at sea level, that's the weight of all the air above us. Now, you might think air doesn't have weight, but maybe in the summertime you rolled down your window in your car and you pulled your hand out your window, and you move your hand around. You can feel the wind blowing on your hand, causing it to move around. And so these are all equivalent units. 101.3 kilopascal is 1 atmosphere. That will push mercury in a barometer up 760 millimeters. And if you're airing up your bike tire, that's equivalent to 14.7 psi. On your car, you probably have an air pressure in your car tires of about 32 pounds per square inch or 32 psi. On your bicycle, if it's a 10-speed, maybe 55 or 60 psi. All of these are, again, units of pressure. Pressure has units of a certain force, such as newtons, divided by an area, meters squared. So who came up with this idea of a barometer? Well, his name was Evangelista Torricelli. I'm sure I'm mispronouncing that. But he said here, we live submerged at the bottom of an ocean of air. Now that's pretty cool to understand that air actually has weight back in the 1600s. So what he came up with was this instrument called what you and I would call a barometer. And that name barometer, if you break it down, comes from the baro, meaning weight, and meter, to measure. So it's the way to measure the weight of the air. So here's, in a very simplistic diagram, what a barometer will look like. You have a tube that's been evacuated. Here you create a vacuum. Then you push that into a dish full of, let's say, mercury liquid. Now, as the air pressure pushes down, that's these two arrows, as the air pressure pushes down, then the mercury is pushed up. The harder the air pushes down, the farther up the mercury gets pushed. There is another type of barometer. It's called an aneroid barometer. This has different metals in here that expand and contract differently with pressure. And this is what would be used on an aircraft to figure out altitude or how high up the plane is flying. They're not going to be carrying a mercury-filled barometer. That would be much too dangerous if it were to spill out. So how do we make a barometer? Again, we start with a container, a dish. We fill it up with some mercury. And then we take a tube that we suck all the air out of, so it's been evacuated. And then we stick that into the mercury. And then we simply let air pressure work. As air pressure pushes down, that mercury is pushed up. The higher up the mercury goes, the higher the air pressure. It is worth noting that the barometer is open at the bottom, so if this whole barometer were to lay sideways, it would spill out the mercury. So that would be a no-no. Don't tip the barometer over. We're simply looking at a little one by an author, a better drawing of that barometer. And I wanted to just compare for you why we put mercury in a barometer, even though we know it is toxic, why we don't use water. Well, the difference is mercury is extremely dense metal. and it's a liquid at room temperature, so it'll still be able to be pushed up and down through the tube. If we were to instead use water, the column of water would need to be 34 feet tall. Now I've drawn here for scale a 6-foot tall man, so you can imagine how tall that barometer would be. It would be 3.5 stories tall. That's simply not practical, so mercury is used instead. This is just showing you 5, 10, 15, 20, 25, 30 feet plus 4 more feet, kind of giving you some perspective of how tall that water column would need to be. Now, if you were to take the barometer at sea level, we said it would measure 1 atmosphere, or 760 millimeters. If you were able to trek that to the top of Mount Everest, why you would ever choose to do that, I have no idea. But if you did, the air is so much thinner, there's so much less air pressure as you go higher up, the barometric pressure would be a mere 253 millimeters. It's like 1/3 as much air. What that means is if you were to climb on top of Everest, basically every breath you take now, you'd have to take 3 breaths on Mount Everest to equal 1 breath here at sea level. Now this is oftentimes why premier athletes train at altitude, and they go to Colorado Springs, Colorado Springs, Denver is called the Mile High City. So if you can train at a mile of altitude high and get your body to perform well at low oxygen levels, then when you get down to closer to sea level, it's as though you have an advantage because you're now breathing more oxygen and you will just perform so much better. I've added a little chart here so you can see what fraction of the atmosphere there is as you go up. So you can see that to be 1/3 of the atmosphere, you got to be about 27,000 feet high. That's the height of Everest. Okay, that would be, commercial air flight would be 30 to 50,000 feet. So if you're flying at 50,000 feet up, you're only getting 1/10 of the amount of oxygen. Now, that maybe makes sense why the planes like to fly that high for international flights, because the air is thinner, there's less resistance against the aircraft. All right, let's keep moving here. I want to make sure we understand the difference between the term boiling and evaporation. They both are a phase change involving a liquid turning to a gas. Evaporation is a very slow process. I'm going to call it evolutionary, where some molecules get enough energy to push to the surface. Not all, just the ones on the surface. Now, evaporation can happen at any temperature. If you have sunlight shining on a puddle of water, well, some of those water molecules on the surface are going to gain kinetic energy and escape. Now, you are not boiling the water. It can be maybe 75 degrees Fahrenheit, but evaporation will still occur. Now, that's different than boiling. Boiling point, or the normal boiling point, is defined as when the atmospheric pressure, that is the pressure pushing down, is equal to the vapor pressure, the pressure pushing up from the liquid. When those are equal, all of a sudden these molecules can just escape in mass, and we call that the boiling point. So it's very, very fast. So air pressure, I told you, is about 14.7 psi. I'm going to round that to 15 psi pushing down. As soon as the vapor pressure pushing up is 15 psi, we've reached the boiling point. Now, sometimes you'll get some beautiful flowers, maybe for prom or something, and you want to keep them. You can actually freeze dry them. The process is called lyophilization. And basically, you take the flowers, you put it in a container. It's a special instrument that pulls all the air out of the inside. It creates a giant vacuum. And by creating a vacuum, whatever water is in the plants is not being pushed into the plants, and the water just instantly boils out of the plants. So in a very short period of time, those flowers can be freeze dried, and where they can be then kept for years and years without rotting. Well, let's look at this graph here. Let's discuss this. We're looking at the vapor pressure of 3 different liquids: chloroform, ethyl alcohol, and water. Now, water you're familiar with. Ethyl alcohol is what adults will consume in a celebratory fashion. That would be like beer or wine is ethyl alcohol. And then chloroform, that chloroform is kind of a nasty material. This is what people would have used to maybe put in a rag and hold over somebody's mouth, and then they would pass out from asphyxiation from the chloroform. It used to actually even be used in surgery, let's say in the Civil War time, but sometimes if it was held over the person's mouth too long, they would actually die. So it's not used today for any kind of anesthesia. Now, what we're looking at is the pressure of the vapor of these gases versus the temperature. And in all cases, as the temperature increases, the vapor pressure increases. Now, if you look at, I've stopped my graph going up to 101.3 kilopascal because that's atmospheric pressure or the normal boiling point pressure. So look, water will exert a vapor pressure of 101.3 kilopascal at 100 degrees Celsius. And that's what we define as the boiling point of water. Ethyl alcohol will boil sooner than water. It will boil at 78.4. Chloroform is extremely volatile or evaporates very readily, and it will boil at a mere 61.3 degrees Celsius. Now, if we were to look at and take our barometer up to the top of Mount Everest where the pressure is 253 millimeters of mercury, well, let's convert that into kilopascal. So here we go. So maybe you remember the first slide said that every 760 millimeters of mercury was equivalent to 1 atmosphere or 101.3 kilopascal. By setting up this conversion factor, millimeters of mercury cancel like that, and I'm left with a unit of kilopascals, 33.7 kilopascal. So I'm going to draw that line, 33.7 kilopascal, onto my chart, make it go horizontally until I hit the line with water, and drop it straight down. And it looks to me like water would literally boil on top of Mount Everest at about 72 degrees Celsius. Now, that would be maybe cool bath water, and that's where it's going to boil. You can imagine if you were trying to cook food, first of all, you wouldn't be able to find wood to burn, but if you had wood to burn to boil water, then when the water's boiling, you'd be cooking your food at about 70 degrees Celsius. It would take forever to heat that food up on top of Everest. Now, just a little aside story. If you were, I'm not sure if you know this, but about 1 out of 10 people that try to summit Mount Everest end up perishing and die in that attempt. And rarely do they take the bodies off the mountain because it's so physically exerting. They found a body recently, maybe 10 years ago, that had been on the mountain for over 80 years. And the person looked as though they were just sun-bleached and sleeping. There were no bacteria on the mountain to decompose because bacteria need water. So the water had basically lyophilized. He's been freeze-dried on the mountain and very well preserved. We only found his body after the climate change started to warm up. These glaciers that had been there for decades finally started to melt, and then they found their body. And you can Google that if you're curious about such things. All right, well, we've already looked at this slide. I'm not going to say anything more about that one. Let's see. Let's go ahead and we'll stop there, and I'll pick up manometers a little bit later in another performance for you. All right, take care. Bye-bye.